Acknowledgement. First and foremost, I'd like to thank Department of Physics and Dr. C.P. Sir of Namche Government College and Sikkim University for providing me such a platform to make a video for partial fulfillment of BSc Honours on Physics at 6th semester February to July 2021. My name is Nunam Subba and my roll number is 18NS0013, and this topic is carrying 25 marks instead of 25 practical examination or sessional B for our examination. Contents, topic and page number. Introduction 4. History 5. What is Bose-Einstein condensate 6. Bose-Einstein condensation 7 to 14. Theory and first experiments 15 to 17. Calculation 18 to 21. Application 22. Conclusion 23. Bibliography 24. Introduction. Bose-Einstein condensation is a quantum phenomenon in Bose gases in which a large number of bosons simultaneously occupy the ground state of a system. Bose-Einstein condensate was predicted in 1925 by Bose and discovered experimentally 70 years later by Wyman, Cornell, and Catley, who shared the Nobel Prize for the discovery in 2001, a state of matter in which atoms and particles are chilled to such low energies that they condensate into a single quantum state. The atoms are bosonic in nature, that is, their total spin must possess an integral value, such as 0, 1, 2. Particles, like everything, into a regime where the wave properties emerge. The wavelength, called de Broglie wavelength of an atom, is related to its temperature. The colder the atom, the longer the wavelength. At room temperature, atoms can be treated like billiard balls bouncing around. At low temperatures, the wavelengths become longer and so the wave properties become relevant. For sufficiently low temperature, a few millionths of a degree above zero temperature, the bosonic atoms effectively become overlapping waves that share the same phase. The atoms become a BEC which has quantum mechanical behavior. History. The Bose-Einstein condensate was predicted by Satyendra Bose and Albert Einstein in 1920s. Hence the name. It is a state of matter in which all atoms occupy lowest quantum state, ground state, and in 1924 S. N. Bose founded quantum statistical treatment of photon, and in 1924/1925 Einstein extended Bose's idea to material particles, predicted BEC in an ideal quantum gas. BEC was first noted to exist in liquid helium. For their observation of BECs in dilute neutral atomic gases, Eric Cornell of NIST/GILA, Wolfgang Catley of MIT, and Carl Wieman of Colorado/JILA received the 2001 Nobel Prize in Physics. While BEC is most often used in the content of neutral atoms, the boson particles can of course be something other than an atom. Examples of these non-atomic species include copper pairs, pairs of electrons participating in the superconducting state, or exciton consisting of an electron-hole pair. What is Bose-Einstein condensate? High temperature T, weak interaction gas which described with thermal velocity V, number density n, distance between atoms d, low temperature T, quantum mechanical description. Lambda dB equals to under root h square slash 2 pi mk bt. De Broglie wavelength with Planck constant h, Boltzmann constant kb, and mass of the atoms m. T equals to Tc, wave packets stacked to overlap and form a BEC. T equals to 0, K, pure BRC described by one single wave function. Bose-Einstein condensation. Bose-Einstein condensation is an exotic quantum phenomenon that was observed in dilute atomic gases for the first time in 1995 and is now the subject of intense theoretical and experimental study. In 1924, the Indian physicist Satyendra Nath Bose sent Einstein paper in which he derived the Planck constant for black body radiation by treating the photons as a gas of identical particles. Einstein generalized Bohr's theory to an ideal gas of identical atoms or molecules for which the number of particles would become locked together in the lowest quantum state of the system. We know that this phenomenon called Bose-Einstein condensation (BEC) only happens for boson particles with a total spin that is an integral multiple of h. The Planck constant divided by 2 pi. This Bose condensate and the process of condensation itself was predicted to many usual properties, and for years experimenters have tried to produce Bose-Einstein condensation in the laboratory. Finally, in 1995, groups at JILA, a laboratory run by National Institute of Standard and Technology (MIT), obtained compiling evidence for Bose-Einstein condensation in dilute atomic gases. Both the Boulder and MIT groups and a group at Rice University in Houston, Texas, has since improved the technique for creating and observing this exotic quantum phenomenon, and rapid progress has been made in understanding its dynamic and the thermodynamic properties. At MIT, we have been recently verified the features that Bose condense atoms are laser-like, in other words, that the matter waves of the atoms are coherent. In this experiment, we have succeeded in observing coherence directly and have demonstrated a rudimentary atom laser that generates a beam of coherent atoms in analog to emission of coherent photons by an optical laser. At the same time, theorists have clarified many fundamental issues and have developed powerful methods to simulate real systems. We can see the figure. The set-off for evaporative cooling from the cloverleaf magnetic trap at MIT, the center curvature coils provide axial confinement, while the other coil, the clover leaves, or gradient coil. And there we can see bias field coil, radio frequency antenna, escaping atoms. Order range in the ground state. The dynamical behavior of a gas at room temperature is not affected by the fact that one atom cannot be distinguished from another. In accordance with the Heisenberg uncertainty principle, the position of an atom is smudged out over a distance by the given thermal de Broglie wavelength. Lambda dB equals to 2 pi h bar square by kbm T to the power half, where kb is the Boltzmann constant, m is the atomic mass, T is the temperature of the gas. At room temperature, the de Broglie wavelength is typically about 10,000 times smaller than the average spacing between the atoms. This means that the matter waves of the individual atoms are uncorrelated or disordered, and the gas can thus be described by classical Boltzmann statistics. As the gas is cooled, however, the smearing increases and eventually there is more than one atom in each cube of dimension lambda dB. The wave function of adjacent atoms then overlap, causing the atoms to lose their identity, and the behavior of the gas is now governed by quantum statistics. Bose-Einstein statistic dramatically increases the chances of finding more than one atoms in the same state, and we can think of the matter waves in a Bose gas as oscillating in concert. The result is Bose-Einstein condensation or microscopic occupation of the ground state of the gas. In contrast, fermions particles with a total spin of n plus 1 by 2 h, where n is an integer, cannot occupy the same quantum state. Einstein described the process as condensation without interaction, making it an important paradigm of quantum statistical mechanics. The density distribution of the condensate is represented by a single macroscopic wave function with a well-defined amplitude and phase, just for a classical field. Indeed, the transition from this order to coherent matter waves can be compared to the change from incoherent to laser light. Chilling the atoms. Bose-Einstein condensation has been cited as an important phenomenon in many areas of physics, but until recently the only evidence for condensation came from studies of superfluid liquid helium and exciton's in semiconductors. In the case of liquid helium, however, the strong interaction that exists in a liquid qualitatively alter the nature of the transition. For this reason, a long-standing goal in atomic physics has been to achieve BAC in a dilute atomic gas. The challenge was to cool the gases to temperature around or below 1 microkelvin while preventing the atoms from condensing into a liquid or a solid. Efforts to Bose condensate atoms began with hydrogen more than 12 years ago. In this experiment, hydrogen atoms are first cooled in a dilution refrigerator, then trapped by a magnetic field and further cooled by evaporation. This approach has been very close to observing BC but is limited by the recombination of individual atoms to form molecules and by the detection efficiency. In the 1980s, laser-based techniques such as Doppler cooling, polarization, gradient cooling, and magneto-optical trapping were developed to cool and trap atoms. This technique profoundly changed the nature of atom physics and provided a new route to ultra-cold temperature that does not involve cyclogen. Atoms at sub-millikelvin temperatures are now routinely used in a variety of experiments. Improved techniques in magnetic trapping. For evaporative cooling at work, the atoms must be thermally isolated from the surrounding This must be done with electromagnetic fields since at ultra-cold temperature atoms stick to all surfaces. The best method for alkyls is magnetic confinement, which takes advantage of the magnetic moment of alkyl atoms. After the atoms are trapped and cooled with lasers, all light is extinguished and a potential is built up around the atoms with an inhomogeneous magnetic field. This confines the atom to small region of space. Atoms can only be cooled by evaporation if the time needed for pre-thermalization is much shorter than the lifetime of an atom in the trap. This requires a trap with tight confinement since these allow high densities and hence fast pre-thermalization times. For this reason, the first experiment that observed BC used so-called linear quadrupole traps which have the cheapest possible magnetic fields. This technique do indeed produce high density and fast evaporation, but with one major problem: the magnetic field is zero at the center, which causes an atom to become disoriented and lose the alignment of its magnetic moment. Since a magnetic field can only confine atoms with magnetic moments that are antiparallel to the field, this spin flip results in a distortions loss of atoms from the trap. Both the Boder and MIT groups found ways to circumvent this problem. The Boder group added a rotating magnetic field to keep the atoms away from the hole, while we plugged the hole with a repulsive force from a focused laser beam. Both of these schemes were successful but had major limitations. In March 1996, we observed BEC in a novel cloverleaf magnetic trap that overcame this limitation. This trap is a variant of the Lofi-Pritchard trap, first suggested back in 1983, and has a non-zero magnetic field at its center to avoid the loss of atoms. The confinement is tight in two directions and relatively weak in the third. Spherical trap clouds. The novelty of the trap lies in the cloverleaf winding patterns of the coil, which allows excellent optical access to the simple for the laser cooling and trapping, and for probing the condensate. The design has proved to be reliable and versatile, and most of the experimental results described here were obtained with this trap. In view of the efforts that has gone into designing traps in recent years, it is rather surprising that the most suitable configuration dates back over 13 years. Evaporation can be readily achieved in magnetic trap using electron spin resonance, the magnetic moment trap using electron spin resonance. The magnetic moment of trap atoms are flipped by applying a radio frequency field in resonance with the energy difference between the spin down state. The frequency of the field is adjusted so that it only affects the atom at the edge of the cloud in an harmonic oscillator potential. These atoms have the highest energy. When the moment of these atoms are flipped, the magnetic force becomes anti-trapping and the atoms are expelled from the trap. As the cloud cools, it stings towards the center of the trap, so the frequency of the radio frequency field must be continually reduced to maintain evaporation at the edge of the cloud. Observing condensation. Trap condensate are very small and optically thick, so they are difficult to observe in the trap. The first observation of BC were made by switching the trap off and allowing the atoms to expand ballistically. The laser beam in resonance with an atomic transition was then flashed on, and the resulting absorption of light created a shadow that was recorded by the camera. This snapshot of atomic position indicates how much the atom has expanded since they are released from the trap, and hence it records their velocity distribution. The atoms in the condensate expand very little because they are in the lowest energy state, and the dramatic signature of Bose condensation was thus the sudden appearance of a sharp peak of the atoms in the center of the image. Absorption imaging is inherently destructive because the atoms are released from the trap. Moreover, the absorbed photon also hit the atom. In early 1996, we observed a Bose condensate non-destructively using dark ground imaging, a technique that relies on dispersion rather than absorption. Dispersion and absorption are conveniently described together by a complex index of refraction. The imaginary part of the index describes the absorption of photon from the probe beam, followed by inelastic scattering of light through large angles. The real part corresponds to coherent elastic scattering through small angles. This dispersive scattering alters the phase of the light, since the light is only slightly deflected. The technique is virtually non-perturbative. The key point is that if the probe laser is detuned sufficiently far from any atomic resonance, dispersive scattering dominate absorption, and the condensate then simply look like a piece of shaped glass, in other words, like a lens. Theory and first experiments. The theoretical study of trapped weakly interacting Bose gases has a long history, starting in 1950s with the pioneering work of Gauss and Pitaevsky on the microscopic wave function for such systems. The past year has seen a dramatic increase in the number of papers devoted to trapped Bose gases, indicative of many unsolved and intriguing questions that are attracting the interest of the scientific community. Roughly speaking, there are two aspects to the theoretical research. On the one hand, there is the solution of many body problems in the case of many atoms occupying the ground state. The challenge is to understand how the interatomic forces modify the structural properties of the condensate, such as ground state configuration, dynamics, and thermodynamics. The second issue of great interest is the study of coherence and superfluid effect in this novel system. As you can see, there is a graph plot between condensate wave function and radial distance, in which it is decreasing. Figure theoretical calculation of the condensate wave function versus radial coordinate for the cloud of 500 rubidium atoms. The solid line corresponds to the solution of Gauss-Pitaevsky equation, which is the Schrödinger equation. Critical studies of the structural properties has been stimulated by the recent availability of experimental data. For the dilute Bose gas, interaction efforts are simplified by the fact that collision takes place only between pairs of atoms and can be described in terms of single parameter, the S-wave scattering length, which is most cases is a distance comparable with the range of interaction. This situation is in stark contrast to the complex interaction that exists in liquid helium. However, an important message emerging from the recent theoretical work is that two-body interatomic forces in condensate can be significant even though the gas is dilute. In the Schrödinger equation for the condensate wave function, the significance of interaction depends on the size of interaction energy per atom compared with ground state energy of the harmonic trap. This ratio is the function of Na by AHO, where A is the S-wave scattering length, AHO is the amplitude of oscillation of a particle in the ground state, and N is the number of atoms. Although A by AHO is typically about 10 to the power minus 3, N can be approximately 10 to the power 7, so interaction can strongly modify the ground state wave function and the ground state energy. This prediction dependence of the energy on the number of atoms have been verified by experiments at both Borders and MIT. From the time-dependent Schrödinger equation, it is possible to investigate the normal modes of oscillation of a Bose condensate. These are analogous to the phonon and rotor excitation that have been extensively studied in superfluid. Historically, understanding collective quantum excitation has played a crucial role in explaining the properties of superfluid liquid helium and was the subject of pioneering work by Lev Lander, Nikolai Gololibov, and Richard Ferment. For a trap Bose gas, the equation of motion have a form that was derived by Bogoliubov in 1947, and recently these have been studied extensively. When parameter Na by AHO is very high, the equation takes the simple form of the hydrodynamic equation for the superfluid. For an isotopic harmonic trapping potential, the frequency omega of the quantum excitation is formed to follow the dispersion law. Omega equals to omega naught 2n squared by 2nl plus 3n plus l to the power 1 by 2. When omega naught is the frequency of the trap, n is the number of nodes in wave function along a radius of the trap, and L is the angular momentum carried by the excitation. This should be compared with omega equals to omega naught 2n plus L for particles that do not interact. The role of the interaction is particularly important in the surface mode n equals to 0, where they reduce the energy of the excitation from omega equals to omega naught by 2 omega equals to omega naught slash half. The hydrodynamic equation can also be solved analytically for an isotopic trap and have provided useful prediction for the experiment at Boulder and MIT. In this experiment, the condensate were gently shaken by modulating the magnetic trapping field, including oscillation in the shape of condensate. Experiment at MIT verified the theoretical prediction for the frequency of this mode to 1%. Indeed, the measurement of the internal energy and the frequency of collective excitation carried out at both Boulder and MIT have provided the most spectacular and convincing proof of the importance of interaction in condensates. Calculation. For an ideal Bose gas of n particles in volume V, the most probable number of particles is given with energy epsilon I is given by Bose-Einstein statistics as Ni equals to Gi by e to the power alpha plus beta epsilon I minus 1 equals to Gi by e to the power epsilon I minus mu kt minus 1. N equals to summation Ni equals to summation Gi by e to the power alpha plus beta epsilon I minus 1 n equals to integrating 0 to alpha limits g epsilon d epsilon equals to e to the power alpha plus beta epsilon minus 1, which is equation number 1. G epsilon d epsilon equals to density of state, and in three-dimensional G epsilon d epsilon equals to 2 pi v dot 2 m by h square whole to the power 3 by 2 epsilon to the power 1 by 2 d epsilon, equation number 2. Using equation 2 in 1, we get n equals to 2 pi v dot 2 m by h square to the power 3 by 2 limits 0 to alpha integrating epsilon to the power 1 by 2 d epsilon by e to the power alpha dot e to the power beta epsilon minus 1. Let z equals to e to the power minus alpha, n equals to 2 pi v dot 2 m by h square to the power 3 by 2 limit 0 to alpha integrating epsilon to the power 1 by 2 d epsilon by 1 by z e to the power beta epsilon minus 1. Put x equals to beta epsilon equals to epsilon by kt, epsilon equals to x kt, d epsilon equals to kt dx. Using the above equation, 3 can be written as n equals to 2 pi v dot 2 m by h square to the power 3 by 2 limit 0 to alpha integrating x to the power 1 by 2 kt to the power 1 by 2 kt dx by 1 by z e to the power x minus 1. N equals to 2 pi v dot 2 m by h square to the power 3 by 2 kt to the power 3 by 2 integrating 0 to alpha x to the power 1 by 2 dx by 1 by z e to the power x minus 1. N equals to v 2 pi m kt by h square into to the power 3 by 2 bz, equation number 4. Bz equals to 2 by under root pi 0 to alpha integrating x to the power 1 by 2 dx by 1 by z e to the power x minus 1. Bz equals to 2 by under root pi 0 to alpha integrating z x to the power 1 by 2 dx by e to the power x minus z. Bz equals to 2 by under root pi 0 to alpha integrating z x to the power 1 by 2 dx by e to the power x into 1 minus z e to the power minus x. Application. It is used in building of atom laser, which could have applications ranging from atomic scale lithography to measurement and detection of gravitational fields. Quantum information processing concept of quantum computer. Precision measurement by development of most sensitive detector using BC. Development of optical lattice, which would be easily modified by varying the interplanar spacing, etc. IBM's binding and rotor nanocenter have been able to achieve the BC at room temperature using a special development polymer or laser and some mirrors. Bose-Einstein condensate could be used to observe quantum mass acquisition. It is used to develop stochastic model of arthropod population. These are compared to modern based on classical Maxwell-Boltzmann statistics. Conclusion. We conclude that Bose-Einstein condensation of charged particles in a strong magnetic field is possible and leads to several new and interesting phenomena as the occurrence of phase transition in presence of an external magnetic field without a critical temperature. For low field intensity we have usual condensation, and for very strong fields condensation is manifest again. The condensate in the strong magnetic field suggests the existence of superconductivity in extremely strong magnetic fields and the existence of a ferromagnetic superconducting phase. This was interest in condensed matter physics. In astrophysics and cosmology, we have also interesting consequences. It gives support to the conjectures existence of superfluid and superconductive phase in neutral star. It suggests also that at the electroweak phase transition, extremely strong magnetic field (MAR) arise as a consequence of the condensation and self-magnetization effects of the medium. Therefore, a Bose-Einstein condensation is a state of matter of a dilute gas or boson cooled to temperature very close to absolute zero. Examples are superconductor and superfluid. Superconductors conduct electricity with virtually zero electrical resistance once current is started. It flows indefinitely. The liquid in a superfluid also flows forever. In fact, there is no friction. Bibliography. Help from Internet www.google.com, www.wikipedia.com. Following links have been used in the completion of this project. https://en.m.wikipedia.org, physicsworld.com